There we go. All right. So, when we're talking about atoms and we're talking about molecules, these things are very, very small, right? Are you going to be measuring out 1, 2, 3, 10, 20 atoms or molecules? No, it doesn't make any sense, right? So when you measure out some amount of atoms or molecules that's actually a reasonable amount, this is going to have to be a pretty big number, okay? Specifically, it's going to be something on the order of 6 times 6.02 times 10 to the 23rd of those, okay? And that would be like a small cup worth of basically any molecular atom, okay? So when we talk about molecules and atoms in a way that's actually going to be meaningful, that we're going to do stuff with it, that we can measure it out in lab, we need to have packages that we can talk about them in. Like saying I have 4 dozen, okay? Or I have 5K, okay? Again, those would be packages of those, right? Or for example, you probably don't normally like buy individual Tic Tacs or individual candies, right? You typically would buy them in bags. They would have like 50 or something, right? Yeah. And again, these are just packages. And so the same thing exists in chemistry. This is called an Avogadro's number. That's the number for the package that we're going to use. 1 mole of that number. So 1 mole is that number of items. So if I have a mole of eggs, then how many eggs do I have? 6.02 times 10 to the 23rd. Anybody know what day it is today? The 23rd of October. 10/23. Guess what today's is called? Mole Day. Happy Mole Day, by the way. Okay. So we learned about moles on Mole Day. That was a really good timing, wasn't it? It was not on purpose. I wish it was, but it was not. All right. So again, moles are just packages. It could be of anything. It could be a mole of pennies. It could be a mole of atoms. It could be a mole of molecules. It doesn't really matter, okay? It is just a package. And in that package, there is 6.02 times 10 to the 23rd items, okay? Whether that's atom, molecules, whatever. This is referred to as Avogadro's number. It's named after Avogadro, which was an Italian physicist, 1776 to 1856. All right, so 1 mole of an element would be 6.02 times 10 to the 23rd atoms of that, right? 1 mole of carbon would be. Very good. 1 mole of sodium. Very good. Yeah, you'll use it enough that you will memorize it eventually if you haven't already. Yeah. All right, so we can write this as an equality or conversion factor if we want. 1 mole equals that number of particles. This would be 1 mole over that number of particles, or that number of particles over 1 mole, right? Okay. So if we can calculate, we can use this to calculate how many molecules would be in a mole of a substance. So how many CO2 molecules are going to be in 0.50 moles of CO2? Yeah, 6.02 times 10 to the 23rd times 0.5, right? Or divide by 2, either way you want. Okay, so we can again do it as a conversion factor if we'd like. And then we take the 0.5 times 6.02 times 10 to the 23rd. If you want to save yourself some time writing this in a calculator, is there a shortcut? Yeah, you can just take 0.5 times 6.02 and then write the times 23, times 10 to the 23. Because the order of operations allows you to do this first, right? So I can just do that and leave the times 10 to the 23rd alone. Okay, so that's going to give us 3.01 times 10 to the 23 molecules of CO2. All right, I'm going to go ahead and give you a problem what is the number of atoms in 2 moles of aluminum? How many atoms is in 2 moles of aluminum? Anybody ready? Okay, everybody good? All right, we ready? 2 moles of aluminum, how many atoms? Okay, don't forget to join if you haven't already. Okay. Okay. All right, so I'm gonna get going. Ready, set, go. Okay. All right. So, not letting you join? Okay, so what are we doing here? 2 times what? 6.02 times 10 to the 23rd, exactly. We can actually just take the 2 times 6, right? In which case that would be 12. Then that would be times 10 to the 23rd. And so that would be 1.2 times 10 to the 24th. Did I break your math in your head? Yeah. Okay. All right. And so it is 1.2 times 10 to the 24th. This right here, by the way, the 3 times 10 to the 23rd, that'd be half, right? Okay. And so again, it's 2 times 6 times 10 to the 23rd. 2 times 6 is 12. We can make that 1.2, and that'd be times 10 to our 10 to the 23rd, right? Which would be another 10. Okay. Let's try this again. So what is the number of moles of sulfur in 1.8 times 10 to the 24th atoms of sulfur? So in this case, I'm going to give you the number of atoms, and you need to figure out moles. 1.8 times 10 to the 24th atoms. So, if I give you 36 eggs, how many dozen eggs do you have? 3. So I've given you here 1.8 times 10 to the 24th. Okay? Another way of saying that is I've given you 18 times 10 to the 23rd. Right? You guys having trouble with that? Okay. What does 10 to the 23rd or 10 to the 24th mean? It's 10 times 10 times 10 times 10, 24 times, right? Okay. So I can always take a 10 out of that and go and move that over. Okay. So 1.8 times 10 to the 24th is the exact same number as 18 times 10 to the 23rd. Okay. Okay. Now, if I take that number, what is the number that is in a mole? 6, yeah, 6 times 10 to the 23rd, right? That's the number of items in a mole. And so I just need to divide my number here, 1.8 times 10 to the 24th, divided by that 6.02 times 10 to the 23rd, right? Or an easier way to see it is 18 divided by 6. Okay, and so that is 3 moles. Very good. Okay. Now, that's what that looks like when you work that out, by the way. Right there. So it's just, we can use it as a conversion factor. 1.8 times 10 to the 24th atoms, that's what we were given. And the relationship between moles and atoms is 1 mole is 6.02 times 10 to the 23rd, right? Okay. We want to go out of moles, or we want to go out of atoms into moles, and so we put atoms on the bottom so they cancel. And that would give you 3 moles. Okay. Okay, both of the ways of looking at this work the exact same way. And that's because both of them are just using this as a conversion factor, okay? The only new thing I'm teaching you here is what is a mole, right? The definition of a mole. It's the same conversion factor problems as we've been doing before. Okay, so this right here is aspirin. Notice this formula for aspirin. When I look at that formula, how many carbons are in a aspirin? Yeah, there's 9, right? How many hydrogens are in aspirin? 8, very good. How many oxygens? 4, very good. Okay, and so these are the subscripts in your chemical formula. They always meant that there's that many of each of those atoms in that chemical formula, right? And that right there gives you the identity of the compound. If I were to say C18, C16, O8, would that still be aspirin? No, that would not be aspirin, despite the fact that that's just 2 times each of those numbers, right? That'd be a completely different compound. Okay, so subscripts are going to be used to write conversion factors for moles in each element. 1 mole of a compound. Right here we're writing these as conversion factors. So there are 9 moles and 1 mole of aspirin, right? Okay, just like in 1 atom in aspirin, there is 9 atoms of carbon, right? Okay. Okay, so let's go ahead and try this out. All right, so how many atoms of oxygen are in 0.150 moles of aspirin? I'm combining my things, aren't I? Okay, I'm gonna let you work on that, and I'll be right back.
I got between 8 and 2.4 times. Yo, I got a B. I got a B.
I was thinking it's either A or W.
I thought it was Let's do it. It's Texas. I think it's B. I'm pretty sure it's B. I think it's B too. I'm already getting here. Okay, because there's 4 in 1 mole, so you just trying to figure out
that 0.6 by 6.0.
So I didn't do the math on my calculator and it gave me that.
There's 4 because there's 4.
6.02 times.
Oh, there's 4.
Can you stop turning with me? In 1 mole. So you
Okay.
like, you have to like.
Oh, so 4 times 1. I might be down one side.
I have no doubt this is the math that I did, but something
Yeah, and
like
then
that.
you would get 0.7.
Yeah.
6.02.
Roger's number was like 6.6.
And then that's not that.
So every do it in that too. No, but see, this is, I know what you're but I'm not like, I know it's more. Okay, I would. It's just like, what you want is like,
None of them have D is just Avogadro's number. So that's an elimination.
I was gonna just buy it. I don't know how my liver's like even solve it. And I went to buy a trigger shop and it was sold out.
No. There is crystals or something. I saw stuff from like 90s.
The number of oxygen in this case. If you multiply that 4 by the number of moles by the answer to that, which is 0.6, and multiply by Avogadro's.
What's the answer?
Oh, see, I got B. I got C. So.
Okay. So the majority of people got C. There was 2 options that made some sense, right? So how many atoms in this case is what we're being asked, right? Okay, so this needs to be a pretty big number, doesn't it? Okay. Now notice that 2 of these options would actually make sense for moles, right? Yeah. So you can multiply the 0.15 times 4. That would give you the moles of oxygen, wouldn't it? Okay. But we need to do one more step. Once we multiply by 4 to get the moles of oxygen, we need to get that into atoms, don't we? That's going to be multiplying it by the 6.02 times 10 to the 23rd, which is the atoms per mole. Okay. Okay. And so it is 2 steps. Huh?
I feel dumb.
It's okay. Yeah. So it's kind of like saying that we bought a package of 4 dozen eggs. How many eggs do we have, right? So we got to go like, yeah, we have 4 packages, 4 dozen eggs, right? Okay. Okay. Now, molar mass. Now, did anybody notice that Avogadro's number is a weird number, right? 6.02 times 10 to the 23rd. That's not like a nice round number, is it? Everything about that is weird. What happened was we played a trick, okay? Remember that periodic table? There's this mass down here. Before, that was in what? AMU, wasn't it? Okay, that was the weighted average of the atoms in a system, isn't it? And so we had represented that as AMU. That is true. But because Avogadro's number is a weird number, we've actually done something clever, which is that we have same number and the units are grams per mole. Ooh, that's what Avogadro's number does. It's actually the relationship between AMU and grams. Cool, huh? Yeah, clever. Ooh. Huh?
I think you should just not invented it.
Well, then you would have had to have 2 numbers here. Yeah, you would have had one number that's AMU and then another number that's grams.
That's okay.
No. You're not going to think that in a little while. Because guess what I'm going to do? I'm going to make you use it. Ooh. Okay, so remember, when you look at the periodic table, that number is both an atomic mass, right? Weighted average of the atomic masses. And that number is also molar mass. Okay? So it actually is both are the exact same number. They just have different units depending on what you want to use. Okay. So molar mass, this is going to be the mass of 1 mole of an element. It's going to have the same number as the atomic mass. It's just expressed in grams for 1 mole of that element. Okay. And here we actually see the carbon one. Again, that's just that number from the periodic table. Okay. So if we have, for example, 1 mole of sulfur, where do we get the mass for that? We go to the periodic table, we look at sulfur. That is the mass, isn't it? Okay. If we have 1 mole of iron, where do we get the mass? We go to the periodic table, we look at iron. That would be the mass of it, wouldn't it? Okay. Okay, and that's true for all of these. If we have a formula like that, potassium chromate, how would we get the mass for that? We could go on the periodic table, look up potassium, right? There'd be 2 of those, wouldn't there? Okay, we'd look up Cr. There'd be 2 of those. Look up oxygen, 7 of those. Add those together, we have the molar mass for that compound, don't we? Okay, let's try it out. All right, so we have right here lithium carbonate, oftentimes used in the treatment of bipolar disorders, though honestly it's kind of a horrific treatment for it. Yeah. Like, honestly, most people that get on this, it doesn't help them ever get back off. But there is treatments that you can do while people are on this to keep them at baseline. So don't ever let a psychologist stop you at this point. Okay? Okay. Now, lithium carbonate, how would we get the molar mass for this compound? Periodic table, yeah. We're going to look up lithium, right? Okay, right here's lithium. Those are the units, grams per mole. We're going to look up carbon. That's carbon off the periodic table. We're going to look up oxygen. That's oxygen on the periodic table. Okay, what's the next step? You got it. We got to multiply lithium by 2. We multiply the carbon by 1, again, because there's 1 of them. And oxygen by 3. Okay. We'll get these numbers out when we multiply them. What do we have to do to those numbers? Add them together or get the sum, right? So we add them together, and that gives us that right there. Okay. Anybody have any questions? So if I have 1 mole of the lithium carbonate, how many grams do I have? 73.89, right? If I have 2 moles, how many grams do I have? Twice that number, right? Okay. Yeah, something like, very good. Yep. Okay, let's try this out. So calculate the molar mass of C2H6O. What would be the molar mass of C2H6O? Yeah, I'll help you a little. There's the numbers from periodic table. Okay, we got it. Okay, so the first thing you're going to do is you're going to take those numbers from the periodic table, and you're going to do what? Multiply them. 12 times what? 2. Very good. Hydrogen's is 1, so 1 times what? 6. And then oxygen is 16, and so that's times 1, isn't it? Which gives you those. Okay? And those are just these numbers up here, aren't they? Okay. And so the next step you're going to do is you're going to take these and add them together, which is going to give you the total. And so we add those together, 46.08. Yeah. And that's the number of grams that are in 1 mole of that compound. Okay. Now, obviously these numbers here can also be thought of as conversion factors, can't they? You may have noticed they were already set up in a very conversion factor-like manner. Okay? And so, again, 1 mole of a compound equals the mass of that compound. If we write them as the conversion factors, you'll notice that was actually the units we'd been using all the time, grams per mole. And you can flip that so the grams are on bottom. So you can cancel out grams and go into moles. Okay. All right, so a box of table salt contains 737 grams of NaCl. How many moles of NaCl are present in the box? Yeah, it does a lot of random stuff on the screen. Okay. So, how do we figure this one out? Yeah, we get the molar mass, don't we? Yeah, so we need to get that molar mass. That relates grams to moles. If we take that molar mass, we divide the mass by that molar mass, we're going to get moles of the NaCl, aren't we? Okay. And so I'm just adding new types of conversion factors to what we learned in chapters 1 through 4, aren't I? 2 new types. Moles and molar mass. Okay. So, again, we're going to be in grams. We go, what do we have? What do we need? How do we get there, right? We're in grams. We want to be in moles. What do we know that relates grams to moles? Molar masses from the periodic table, right? Okay. We have a formula here. So I take my formula for NaCl, and I'm going to look up my periodic table and go, okay, NaCl. Na has a mass of 22.99. Cl has mass 35.45.
How do you know what to round the mass?
You don't round anything until the end.
Oh.
Yeah. And then that's going to be this number here. Yeah. The reason I just did this is because these would be very long and difficult to see easily on one line. If you do one significant figure more than this, you'll usually be okay-ish. Yeah. My typing's mostly to make it typesetted. Okay, so I add those together. That's going to give me grams per mole for my NaCl, which is molar mass. Now, correctly stated, if anybody goes on to a higher level science, correctly stated, this is not actually technically a molar mass. This would be a formula weight, okay? But for you all, that doesn't matter. They're the same thing. Nobody's going to care if you say the wrong one, okay? But anyways, if anybody was curious. All right, so we're going to take that molar mass here, and it's grams over moles, right? Okay, we currently have a number that's in grams, don't we? Okay, so we're going to take that number in grams, we're going to divide it by the grams per moles, like so. And that's going to give us moles. And how many sig figs do we end up in? 3, yeah, and that's from that number right there. The molar masses should always be high enough sig figs that they should never be what sets you. Though there is a couple cases on the periodic table that have not been weighed out well because they've only existed for a fraction of a second. Yeah. So they didn't have time to weigh them. All right. Any questions on how to do this? No? Okay. Yeah, it's a really simple conversion factor problem, right? I just have added a couple new types of conversion factors. Now I'm going to test you over it. So sample water has a mass of 59.8 grams. How many moles of water are in that sample? By the way, if I'm ever beating a dead horse and you guys are like, I'm good, I'm done, just let me know, okay? Yeah. I'm doing it based off of what my other class has been having difficulties with, but that may not be true for you all, okay? Okay, then I am fine staying with it. You can please ask me questions. If you don't want to actually ask in public, that's what those QA slides are for. I've just been moving past them quickly because there's nothing on them. Yeah. Okay. All right. Everybody, nope, still have 7 people left. Okay. Okay. Okay, I'm gonna move on here in just a bit. Please go ahead and get an answer in if you want to try to submit something. If not, I'm gonna move on. All right. So, the vast majority answered that, and that is correct. Okay. And so, 59.8. Okay. Anyways, the 59.8 is obviously I just took the number from above. So what you need to do here again is going to be, well, what is water? H2O, right? You're going to take water off your periodic table. You're going to add those together. So you have 2 hydrogens, that's 2, plus the oxygen, right? Which is 16. And so altogether that's something slightly over 18. It's a multiple choice. You don't have to actually get the sig figs, right? So then we're going to take that 59.8, we're going to divide it by that 18. That's going to give us a number that's just a bit over 3, or 3.32 moles of H2O. Everybody good? Okay, fantastic. Okay, so let's talk about writing a chemical equation. Now, this is usually referred to as a chemical reaction. But a chemical equation is absolutely literally correct. Okay? So this is a chemical reaction or chemical equation as your book calls it. And it's literally the ingredients you put together and what they produce, right? Now, it literally is an equation. See this arrow thing? It's the same thing as saying equals. Okay? And so if I have 1 carbon on the left, how many carbons on the right do I have to have? Yeah, 1. It has to equal out, doesn't it? If I have 2 oxygens, it has to have 2 oxygens on the products. Okay, so these are the reactants right here. This means it yields, it gives you. And this right here is the products. The reactants are by convention, always written on the left. By convention, products are written on the right. Okay? Because we read left to right in the English language. Now, does that mean that chemists don't ever not do that? No, no. In fact, chemists are going to treat this like it's an equation, like you would in math, right? And so if you were given something that looks like this, what would you do to it? You'd probably end up flipping it at some point, right? And have y on the left just because you're used to it? Yeah. Chemists will do that all the time. We'll just freely flip it to whatever the hell we want it to be. Okay? All right. This delta here, this means that you need heat to get the thing started. So this is actually burning coal. To get this started, we need to actually put in heat. My goodness, what the hell is going on with this thing? Okay. Now, again, that's your chemical reactions. Is everybody comfortable with those parts so far? Okay. Okay, so if we list the states, that's going to be parentheses S for solid, parentheses L for liquid, parentheses G for gas, parentheses AQ for aqueous. Anybody know what aqueous would mean? Yeah, aqua, water, right? Dissolved in water. Okay. That's given a special designator because it's extremely common. The most common solvent on the planet, water, right? Absolutely everywhere. Can't get it out of things. It's a real pain in the butt. Okay, now this right here is how you're going to separate the two in formulas whenever you have two things or more in the reactants or products. So for example, you'd have a reactant plus a reactant, right? Okay. Anybody have any questions about any of those so far? Your handy dandy symbols. Okay, so again, remember that no atoms are going to be lost or gained. You always have to balance an equation. Equations always need to be balanced. And so, whenever you try to balance things, you always want to start on the most difficult things first. Okay? And in general, that's good problem-solving advice, right? Always start on the thing that's going to be the most time-consuming, energy-consuming, the most difficult that you need done, right? Okay, so let's go ahead and write the equation using correct formulas for reactants and products. Okay, so right here we have an unbalanced equation, don't we? All right, so how in the world do we balance this? You okay?
I remember doing this in chemistry, and I almost had heart attack.
Oh. Okay. So leave the simple stuff to last. Okay? That's, if you concentrate on the simple stuff last, it's always going to work out nicely. Right. So in this case, we don't actually have to do anything to that, do we? No. And so we're just going to go through how many sulfurs do we need? 3. And so we put a 3. How many aluminums do we need? 2, and so we put a 2. That's not too bad so far, right? Okay. It can get bad. All right, so okay. All right. So let's go ahead and try these ones. Let's go ahead and state the number of each element of the reactant side and product side. So how many P's are on the reactant side? 4, exactly. How many P's on the product? 4. Now, notice this says they're balanced equations. If you trust that, do you actually have to count them up on each side? No, it being balanced means they're equal on both sides, right? Okay, so how many BRs? 12, yeah, 6 times 2, right? How many BRs over here? 12 again, 3 times 4 to give you 12. And in fact, they have to be, right? They wouldn't be balanced without that. Okay, how many ALs? 2, very good. How many FEs? 2, very good. How many O's? 3, excellent. Okay. So let's balance the chemical equation when solid Fe3O4 reacts with hydrogen gas to produce solid iron and water. Okay. So we're going to be taking, what's our first reactant that we're given here? Fe3O4, very good. Okay. And so that's going to be reacting with what? Hydrogen gas, very good. What's the phase of Fe3O4? Solid, yeah. So I got to put an S, don't I? plus, and then I'm going to be doing H2. Everybody see how I left a big space right there? Okay, why did I leave a space? I'm going to have to put coefficients is what they're called, so I can balance the reaction, right? Okay. Okay, and so that's a gas. Very good. Everybody sort of indicated that. Then I'm going to yield. And what am I going to produce? Solid iron. How do I write solid iron? Fe. And then S. You got it. Perfect. Yep. Very good. And H2O. Water. Now, this one doesn't actually indicate the phase of this water. Typically, water is considered liquid in most situations, but this could actually, if it produced heat, which it likely would, it could be a vapor, water vapor. I'll just put liquid for this one. Now, we're going to go ahead and balance this out, aren't we? Okay, what are the things we want to start with for balancing? Yeah, so we could do iron or the hydrogens, but we want to specifically concentrate on the complex stuff, right? The most complex situation we have to solve in this one is the Fe3O4 versus the H2O. Those oxygens are going to be where we will have any trouble if we do. Okay? Okay, because everything else is off by itself, isn't it? Okay. And so we can just put a number in front of like Fe, and that'll balance out Fe, right? No problem. Okay, and so do we have to put any numbers in front of Fe3O4? No, we don't have to do anything with that, right? How about the H2O? Yeah, what do we need to put? 4, yeah. 4 will give us equal numbers of oxygens. Okay, so that does create a situation for us though, doesn't it? We now have 8 hydrogens on the product side, but only 2 on the reactant side so far. What do we put in front of the H2 then? 4. Yeah, we're going to even those up. And then what's the last number we need to do? 3 in front of the Fe. You got it. Yeah. And that will equal out my numbers of irons. And there we go. Any questions?
Is hydrogen gas always going to be H2?
Yes.
Not just H?
Yeah. Yeah. That's the diatomic gases that make that sort of L shape. Okay? There we go. Okay. So these ones are going to be balancing equations with polyatomic ions. There really isn't much of a difference. The only thing you got to really remember here is that you can't just randomly change numbers within a formula, right? They wouldn't be the same formula, wouldn't be the same compound. Okay, so we have here N3PO4. This is reacting with MgCl2. This is going to give us the product Mg3PO4, and then there's 2 of those. Can everybody see that? Okay. Why is it a parentheses around that PO4, by the way? Exactly. That's that polyatomic ion, right? That it has to stay together. We can't change the numbers otherwise. We'd actually have something different. And this is going to give us NaCl, which is table salt. Okay. Now, how do we get this to be balanced then? Yeah, we're going to have to put those coefficients out front, right? Okay. And so we see here the Na and Cl's, or the Cl's are unbalanced. The phosphates are unbalanced. A lot of stuff unbalanced, isn't there? Okay. And so what's one of the first places we could go ahead and go to here? Yeah, we're going to have to balance things up so odds can get to evens, right? The easiest way to do that typically is to take the odd numbers and multiply them by 2 first. Okay? Okay, so what is the number that needs to go in front of, for example, Na3PO4? The PO4 has to get up to 2, doesn't it? Yeah, so 2 would be the easiest way to fix that. Okay. Okay. And so the next thing we have to do here is we have to go over Mg3PO42. Okay, well, that's going to be a little bit interesting. So what do we need to do for that MgCl2 then? We need to put a 3 in front of it, don't we? So 3. Oops. Okay, and so what's the next part? Mg's are equal, PO4s are equal. Yeah, we gotta go to the NaCl, don't we? Okay. How many NAs are there? 6. How many Cl2s are there? Or Cls, excuse me. Yep, and so we put a what in front of the NaCl? 6. Very good. Very good. Notice that if you do the complex stuff first, everything else takes care of itself eventually. So, okay, I'm going to have you guys do it now. Ready? No more help. My cruelty knows no bounds. Making you do problems. Balanced chemical equations. Oh my. Once you get a bit of practice, you'll be able to do these pretty quickly in your head. But it's okay if it takes you some time working on the page. I do recommend pencils for these though, when you're first learning, okay? It'll save yourselves a lot of scratching. Okay. So, go ahead and answer something if you haven't. Let's move forward. Okay, I'm going to go ahead and move forward. If you haven't answered, please do. Excellent. Okay, so 2, 3, and then the difference between these first two ones is 4 versus 2, right? And that's back to 3. I know I put 2 that are fairly similar, didn't I? Uh-oh. Okay, and it's the one with 4. Yeah. That's because the 2 in front of the Fe2O3 gives you 4 irons, right? And so we have to put a 4 in front of the Fe on the product side. Okay. All right, try this one. We're doing good though. Aluminum. No. An Al with a solid. Yeah. Yeah, you get a lot of glare on that, don't you?
No, I'm just blind.
No, you're good. If you ever want, you can come closer. Though I do recommend not sitting in the desk like right in front of me, which I have had somebody do once. It was weird. It was weird.
Just like having a staring contest the whole class.
Oh yeah, I'm not joking. Like closer than this one here. Like almost the other side of a desk like this. It was tables in the classroom. And it was like an extremely comfortable dinner with a friend. Every lecture. Yes. Like there could have been candles there, and nobody would have said anything. That was really close.
Really a good student or like?
They were nice. Yeah. Yeah.
That doesn't mean they were a good student.
Yeah, they didn't study a huge amount, but they were nice.
Okay.
And they were enjoyable company in the classroom, I guess.
Clearly they had like no awkwardness. No awkwardness about them.
It was a pretty full classroom, but there was another position that they could have sat on. Now that would have been funny. I actually had something not quite. Like, I had somebody sit, like, right there once when there was only 3 people in the class. Which was a little interesting. Okay. All right, folks, and that is correct. Very good. Okay. Did anybody need me to go through why that is this one?
If you're just like writing it down as an answer, you need to put 1 down below.
You don't actually have to put the number in, no. Yeah. Yeah, it's just when I'm writing it, it wouldn't make much sense if I didn't. Yeah. But no. Yeah. You can leave the 1 out. It being there indicates 1, right? Yeah. Yeah. Okay, let's try that one. I know. It's like this is important to go on to the next ones. You can just solve them if you want. You don't have to write them down and everything. That's fair. That's fair. So what you're telling me is I need to give you far more practice problems. So it becomes like something you do in your dreams. That's what you're telling me, huh? Okay.
Hey, you should tell them on your way out that
I have. Yeah. No, I told them that it's gotten worse every week that I've been in here. And I don't think they've sent anybody, so yeah. Yeah. Okay, folks, I'm going to go and move on. If you haven't submitted something, please do. Okay, let's go ahead and go. Okay, and 81% that, and that is correct. Okay, and the big difference here is that if you put a 1 in front of the AL2, that would give you 2 ALs in the front one, right? Okay. Okay. All right, so let's talk about some types of chemical reactions. What is this normally referred to as where I'm burning things like that? Combustion. Yeah, so that is a combustion reaction, isn't it? That's the one everybody usually knows because that's kind of built our world around us, hasn't it? All right, now, the chemical reactions, one method of classifying them is to say combination reactions, decomposition reactions, single replacement reactions, double replacement reactions, and combustion reactions. These actually can have different names depending on who writes out this classification. Okay, this is usually the easiest classification types to understand, though, because the names very directly mean what they do. Yeah. Though, to be honest, their names tell you what they do, and so it's like a semi-memorization. Yeah. So combination reactions, you'll have 2 simple things combining to give you something more complex, just like the name says, right? So they combine to give you something more complex, combination reaction. These are examples of combination reactions. This is actually a combination reaction occurring, which is magnesium burning. Notice this is not a combustion reaction because it doesn't fulfill the definition. Okay? Even though you might be fooled into saying combustion. Okay? Now, this one right here, magnesium burning in the presence of oxygen. Interestingly enough, the camera actually, this is actually what like a flashbang would be made of. So if you were to powder the magnesium and do this reaction, that's a flashbang grenade. Okay? It burns very bright. Has anybody ever seen one of those flares? Yeah, that's a magnesium flare. I'm actually unsure of how they managed to get this so the camera sees it. They must have really dialed down that shutter. So you almost no lights coming through. Usually it blanks out the cameras. Yeah. Okay, this is decomposition reaction. You'll take something more complex and decompose it in something simpler. Okay, decomposition. This is an example of a decomposition reaction, of course. And here we see an example showing it off. And so we have the mercury oxide. It's decomposing in the presence of heat to mercury, the metal, and oxygen gas. That's why there's bubbles up here, by the way. It's bubbling out. Okay? Ooh, it's so pretty. Okay. Single replacement reaction. We're going to replace one thing with another. I know. The name says it all, doesn't it? Not a lot for me to add. One thing gets replaced with another. Okay. Now, this is the example again of the single replacement reaction, where this is a very common reaction where we take an acid and it reacts with a metal. Okay. So in this case, we're reacting zinc with a metal, hydrogen chloride with zinc, which is the metal, and that's going to evolve hydrogen gas that is flammable, by the way. And this will give us zinc chloride, which is soluble in the solution. If you have enough hydrochloric acid, this will eat away all the metal. And you won't have any metal left. This right here is a double replacement reaction, sometimes referred to as a metathesis reaction. Oftentimes this reaction is going to cause precipitation, and people are going to say precipitation reaction. Okay? But it is a double replacement reaction is one of the namings for it. Metathesis is when you want to sound smarter. So if you want to talk about this and sound a little bit smarter, metathesis, okay? Okay. It means the same thing, it's just Greek. Okay. And so double replacement reaction, replace two things. That actually is giving you precipitation here. Everybody see precipitation right there? Where it looks milky? Okay, precipitation is kind of like a snow globe. It's solid, that's still suspended. It hasn't rested out yet. Okay? It's a temporary state. If you let it stay long enough, it will settle out. All right. Combustion next. You have a great day. So energetic. Okay. You all have a wonderful day. I will see you.